Today I'm going to be demonstrating a MSP432 Memory Bank 1 flash example. Memory Bank 1 is a 128 kilobyte memory bank, and we're going to be writing a hex A5 to all locations in that memory bank. It's just a arbitrary value so we can actually see that the flash is occurring correctly. Alright, so let's jump right into the code of how this is implemented. So the first thing I do is hold the watchdog timer. This is just temporary because currently the watchdog timer is not initialized, and so we don't want any premature resets to happen before we have everything configured correctly. We're going to re-enable it down here right before our main processing loop. So it's after everything has been initialized correctly. Next thing I do is just disable all of the interrupts on the device, and again this is just because nothing's initialized yet. The first thing that's initialized are the ports of the device. So we go in here to the port init function, and the first thing it does is call this terminate GPIO function. And this is based off of other examples from TI of how to basically reduce current draw from the device. And all we're doing is just configuring every pin on every port of the device to be an input with a pull down resistor. And if you're wondering where this hex value came from, it's basically just the sum of all of the GPIO pin macros, so like GPIO pin 0 through pin 15. If you add them all up, it equals this value. So it's just saying every pin on that port, just set it to an input with pull down. And also, since this function is basically limiting our current draw on the device, I also just added this high performance mode setting to just normal performance mode. I'm not going to go into too much of how that works, but basically it's just limiting current draw again on the device. Alright, so after the GPIO has been initialized, we're going to reinitialize our port 2 pin 0 through 2 for an output pin. And this is mapped to the tricolor LED. I think it's LED 2 on the device. And we're going to use this to kind of interface with the user by setting the tricolor LED to red whenever we come up from a reset, and again we're going to set it to green once we flash all of memory bank 1, or every time we flash memory bank 1. And after we've initialized it as an output pin, of course we want to set the output to low just to kind of get rid of any unexpected outputs on the LED. And the next port we're going to initialize is port 1 pin 1, and this is mapped to switch 1 on the device, and this will be used to allow the user to manually cause a reset on the device if needed. Alright, so that's it for port inits. The next thing in main that's called is our timer inits. So in timer init, the first thing we do is just set the DCO center frequency at 1.5 megahertz. It can be set higher, but the design constraints were to flash memory bank 1 or 128 kilobytes every 60 seconds, and this is plenty fast to do that, so we're just kind of setting it low. We're also going to set our reference oscillator at 32 kilohertz, and then we're going to set our M clock equal to the DCO center frequency, and then we're going to set our SM clock to the reference oscillator frequency. So we have a master clock of 1.5 megahertz, and the SM clock is at 32 kilohertz. The next thing we're going to do is initialize timer A, or more specifically timer A1 is one we're going to use. And the struct here is how we're going to configure it. So we're going to set it for a SM clock source, so a 32 kilohertz source. And then we're going to divide it down by 64, so we have 32K over 64 equals 500. And then we're going to set our up count to 500, which will essentially cause us to have a 1 second interrupt, essentially, because we're counting up to the same value that it's divided down to. And then we're going to disable the timer interrupt and enable the capture compare interrupt, which will basically give us a compare give us an interrupt every time we count up to the target value. And then we're just going to clear it to initialize the timer. And this target count variable here is how we're going to farther configure our capture compare interrupt. And what it does is basically takes the 1 second count and divides it by 25, so we get a 1 over 25 second interrupt, which is a 40 millisecond interrupt. So basically all of our timer A1 will give us an interrupt every 40 milliseconds is all that's doing. And then of course we're going to configure it to up mode, so it will count up to our target, and then we'll kind of reset and just keep counting up to that. And then we're going to start our counter and enable the interrupt. And it's also important to note that whenever we enable this interrupt, we also need to give it an interrupt to go to, and we're going to use this TA1_0 IRQ handler. And all this does is increment a global variable called 40 millisecond count that we will use later in the program. And if we look up our startup ccs.c file, we've also mapped the interrupt to the TA1_0 ISR. Alright, so the timer A1 is now set up, and now we're going to initialize our watchdog timer, which is a little bit easier to do than the A1. All we're doing is just setting it to the SM clock source, which is a 32 kilohertz source, and then we're going to let it count for 32,000 clock cycles, which essentially give us a 1 second watchdog timer. Alright, so that's it for the timers. The last thing to initialize is our memory, more specifically our memory bank 1. And what we're going to do is set the wait state to 2, and then we're going to set this global variable called buffer, which is defined up here at the top, and it's just a list of 8-bit integers, and we're going to initialize that to our arbitrary hex A5 value for flashing later on. And then we go to this loop here, which basically all it's doing is going through every sector in memory bank 1 and unprotecting it. So it iterates through this list here, which is predefined flash sectors, and just unprotecting them so we can erase and flash them later. So that's it for our memory initialization. So now that everything's initialized, we're going to go ahead and enable our interrupts. And according to our design specifications, we want to turn on a red LED for 1 second on a reset. So what we're going to do is we're going to set our target to our 40 millisecond count, whatever it happens to be right now, plus 25. And since 40 milliseconds is 1 over 25, it's essentially just a 1 second count. So all we're going to do is sit here and turn on our tricolor LED to the red state for 1 second, and after that 1 second has passed, we're going to turn off the red LED. And right before, the last thing we do before we go into our processing loop is, of course, enable the watchdog timer so it can catch us if we start getting stuck anywhere during our flash process. Alright, so it's time for our while loop. You'll see this function a lot, the watchdog timer clear timer, and this is basically just a way to pet the watchdog and say everything's good and reset it. Another function we're going to see often is the delay while pressed function. If we go back to ports, we can see what that does. Basically, all it's doing is checking to see if that switch is pushed, and if it is pushed, we're just going to sit here in this loop. And the purpose of this is to basically say that the user is going to press down the button, and if they hold it for longer than a second, then the watchdog timer will expire and will cause a reset. Alright, and we also, we'll get into this later, but we also set the power state to a known active mode state. That'll be more evident of why we do that later on, so I'll come back to that. Alright, so for every sector, so there's 32 sectors in memory bank 1, and for every sector, the first thing we're going to do is erase that sector. So let's go into this memory erase sector function. So what we're doing is we're just giving it an index of which sector we want to erase, and it's going to use this array called sectors actual. And all this is sectors that are macros that I defined up here in this header file, and it essentially is just the hard-coded memory locations of each sector, since it doesn't accept 2 arguments, so we can't give it memory bank 1 sector 0, we have to give it the absolute value of that address. So each sector is 4 kilobytes, so we just start at the first location and just increment it by 4 kilobytes at a time. So all that erase sector function is doing is basically just erasing that 1 sector and returning. And this while loop, what it'll do, the flash control erase sector function will return true if it was successful, and we'll exit the loop. If it's not, we will stay in here and try again until the watchdog expires and resets us. So if for some reason we can't erase, we will reset again and display a red LED, and the user will know that something happened and we'll go in and debug. Alright, so after everything is erased, we're going to iterate 32 times for 32 sectors. And now we're ready to flash. So we go into this write sector, which is very similar to the erase sector, except now we're giving it our buffer, which is our 4 kilobytes of known hex 85 data, and we're just giving it the address of what we want to write and the length, which is of course 4 kilobytes. And also similar to the erase sector, it will return true if it's successful, and we will exit. If not, we'll sit here in this while loop. Alright, so if we get this far in the code, we were able to write everything successfully, so now it's time to display our green LED to show the user that we were able to flash our memory bank 1. So what we want to do, since we have our watchdog timer, we can't wait 1 second anymore, otherwise we will generate a reset. So what we're going to do instead is wait in 2 half-second increments. So what we'll do is, instead of doing our 40 millisecond count plus 25, we'll do plus 13, which will give us a little more than a second, but it's close enough to our specifications. So what we'll do is we'll just wait for half a second, turn it on, clear the timer, and then try it again. And again, we're like in other places in the code, we're also waiting to see if the user wants to reset here. And after those 2 half seconds have expired, we'll turn the green LED off. And now we'll go into this really long wait loop, which is essentially what this is. Since our specification says about 60 seconds to flash memory bank 1, and this whole process up here probably takes about 8 seconds, like 6 to 8 seconds. We have a lot of breathing room in our specification, so during this time all we're going to do is we're going to set, again, we don't want to do exactly 1 second, but we're doing pretty close. We're doing 40 milliseconds, which gives us 80 milliseconds of breathing room to reset the timer. And during this time, what we're going to do is we're going to go to our low power mode. So essentially what's going to happen is we're in this low power mode, and our 40 millisecond timer fires and wakes us up from low power mode, and then we check our count again and we see it's not time, and then we just go back to low power mode until it is time, until we're past this 23 mark, and then we will clear our watchdog timer and go to the next loop. So essentially this loop will delay for about 46 seconds, which gives us about 54 seconds that it takes for us to flash our memory bank 1. So we still have some breathing room within the specifications. And if we go back up to the top at this set power state, this is why we're setting to our active mode. It's just to make sure that down here, whenever we're switching to our low power mode, that we're back in a known state up here. It's just to kind of verify that everything's okay there. Alright, so now that we've kind of walked through what the code does, let's take a look in the debugger and see what it's doing. So we'll go ahead and build, and let's flash it to our device. Alright, so at this point in our code, set a breakpoint towards the top, and what's all that's happened now is just our initialization, and now we're going to turn on our red LED for 1 second to let the user know that we are coming out of a reset. So let's take a look at that. Disable the breakpoint here. Alright, so we see the LED turned on for about 1 second to let the user know that we're coming out of reset, and now we're ready to go into our main processing loop. So the first thing that should happen is we should get through our erase portion first. And just a kind of heads up here, I did split the video here and just added this or equal 0. And this is just basically a no operation method of just setting a breakpoint. It's just so we can set breakpoints right before and after where the erase and write happen, just for demonstration purposes. So just to let you guys know what that is. Alright, so now at this point, all of our memory locations in memory bank 1 should be erased. So let's go into our header file and grab the first location that we are erasing and pop it into the memory browser here. And so we see here that at the first place we have everything that's all F's, which means that it was erased successfully. And now let's just go to the end and make sure that the last location was erased as well, and we see it has. We see that it's all Fs, and that we are ready to go to our flash portion. So now let's go back to main, and let's run through the flashing loop. Alright, so now we've gone through our flash where everything was set to A5, and now we can see at the last memory location that everything has been set to that arbitrary value, so everything looks like it was written correctly. And let's go back to the original location and see if that was changed as well. And here we can see that everything was also written to A5, so it seems like everything was written correctly in Memory Bank 1. So now the only thing that is left is for us to go and turn on the LED, the green LED, for 1 second to let the user know that we are able to flash correctly and display the green LED. So let's take a look at that. Alright, and we're good. Doesn't look like a reset happened, and we showed the user that we were able to write to those memory locations. So now is for the long delay loop, so we can go ahead and run that through, and we'll just let it run for a little bit just to make sure that it's going through the loop and there's no resets happening. And then we will show a manual reset, which will be demonstrated by, let me set the breakpoint up here at the top, it'll be demonstrated by pressing the switch, so we should be able to just hold the switch down, and there we are, back at the top of the code. So we held the switch down, and it went down here into the delay while pressed function, and just sat there for a while until the watchdog reset us. So now we're back up here to the top, and we should still see all the values written to flash, so let's go ahead and run to right before we erase, just so we can see that the values are still there. We saw the red LED come back on again, and now right before we still see that everything is still A5, or our arbitrary value. So now let's see if the erase will actually occur correctly now that we know we have something to erase. Alright, so it seems like our first location was written correctly, and now let's go back to our last location, which is 3F, and now we see that that was erased as well. And now we'll just verify that we can erase it, so this we'll set it a little farther down, so now we'll go through the erase process and turn on the green LED, and then we'll look at the memory again. Alright, so it indicates that we did, and at the last location it looks like we were able to write again, and at the first location we were also able to write. So everything looks good. Looks like we should be able to write and erase correctly. Alright, so now let's talk about a little bit of the optimization stuff that was done, and we'll let that run through while we're doing that, just so we can maybe see it run through the loop again. It's a long delay, so but we should be able to see it within the minute. So we'll just let that go while we're talking about optimization. Let's go back over here. So the first thing, the primary thing I did was uninitialize ports, which again we talked about before, and I'm not sure why it's still showing up here. This is what the stuff I used was what TI recommended in their documentation to do, so I don't know if it's because I'm not using macros or what, but all of these all of this advice was taken and implemented in the project. We also are using the different size integers, so int I doesn't go above 50, I believe. Yeah, it doesn't go above 50. So we don't need to declare a 32 or 16-bit integer, so we're using smaller integer size there, and throughout the project for indexes and things like that. We have the index here is 8-bit and stuff like that. We also used the optimization assistant, which we should be able to go in here and see. Yes, we have the speed versus size trade-off set to maximum, which is 5 from a 0 to 5 scale, and we also have the optimization level to 3 for inter-procedure optimizations. Alright, and we should be able to go to, we saw the green LED come on there, so it indicated we went back through the main loop again. Alright, So now we look at our optimization assistant, and initially I had it set to 0, which as we can see is not that far off in code size from the stuff we landed at. It's about like 300 bytes, so it's certainly worth it to speed up our code to increase the size by that just a little bit. And we also notice that there's no point in setting it to level 4 because we can set it to level 5 with no code space restrictions there, so we might as well just go ahead and set it to 5. So we have our optimum speed there. So that's it for that. We can run it again just to make sure everything's still good. What it'll do now is kind of analyze everything. So our code size went up a little bit from last time, probably from adding the little the OR equals and stuff like that for debugging purposes. And once again we see that there really isn't that much difference in size between the last and first level, so we might as well just go ahead and set it to the higher value. So that's it for optimization. There's also, we did talk about the low power mode here. We can go into low power mode 3, but we're already drawing so little power from the low power mode, and we're not that constrained in this environment, so low power mode 0 should do the job just fine, especially if we're staying in that for 46 seconds compared to the like 6 to 8 seconds we are actually active in our active mode. Alright, so the last thing I'm going to demonstrate is just the device running in a real-time environment without the debugger. So if we go over to the debug session here, we see that it's not active, and we're just going to plug it in and watch it go. So we have the red LED on boot up, and then we have the green, and now it's back to our wait loop that we saw earlier, and now I'm just going to hold the button down, cause a reset, and now the red LED's back on. We're back in the flash loop, and it's flashed and it's successful. Alright, so that's it guys. Thanks for your time.